For 2008 Form B question 4, we have this function f of x is kx squared minus x cubed, where k is some positive constant. And R is going to be the region in the first quadrant that's bounded by the graph of f and the x-axis. Well, even though we don't know what k is, if we were to factor out an x squared in that function, we would get x squared times k minus x. And since we know this is a cubic function and the leading coefficient is negative, so we know that that's got to start at positive infinity and work down to negative infinity. And it's going to have a double root at x equals 0. So we could assume that the graph looks something like what we see here, where the second x-intercept is going to be at x equals k. And of course the first one is at x equals 0. Alright, so we're looking to find all values of the constant for which the area of R is equal to 2. And the area of that region between the in the first quadrant bounded by the graph of f and the x-axis is given by the integral from 0 to k of kx squared minus x cubed dx. And the antiderivative of that integrand then is kx to the third over 3 minus x to the fourth over 4, and we're going to integrate that from 0 to k. And so we get kx cubed over 3 minus x to the fourth over 4 from 0 to k. And substituting k for x, we're going to get k times k to the third, which is k to the fourth over 3, minus k to the fourth over 4. When I substitute 0 for x, the whole expression will 0 out, so I'm just left with this k to the fourth over 3 minus k to the fourth over 4, and finding a common denominator is going to give me k to the fourth over 12. And I want to find out where that's equal to 2, and that happens when k to the fourth is equal to 24. And so the only way we're going to be able to solve this then is to say that will be true whenever k is equal to the fourth root of 24. And so that's the answer for part A. It couldn't be the negative of that. Why wouldn't it be able to be the negative? If it were the negative of that, we still have to have the root at 0. Well, to say it plain and simple, k has to be some positive constant. And so it's impossible any other way around it. Let's go on to part B. For part B, we want to, for k greater than 0, we want to write but not evaluate an integral expression in terms of k for the volume of the solid generated when R is rotated about the x-axis. And so what we're looking for is to use the disk method to find the volume of the solid created when that region is rotated. We start with finding the surface area of that disk, and it's pi r squared, where r is equal to f of x. And so the volume would be the integral of that area times the small change in x dx integrated from 0 to k. And so we end up with volume is equal to pi times the integral from 0 to k of f of x quantity squared dx, which should give us our value, or the answer. And on an AP test, that should be sufficient. F of x is clearly defined as kx squared minus x cubed. If you wanted to rewrite that, you would end up with v, the volume is equal to pi times the integral from 0 to k of the quantity kx squared minus x cubed all squared dx. And we're done with part B. We'll go on to part C and D in the next video.